Welcome back to the deep dive. Today we're tackling a bottleneck that pretty much dictates the entire pace of modern AI development right now.
Yeah, it really does.
Because it's not just about raw compute power anymore. I mean, it is, but it's really about memory. Specifically, we're talking about the context window.
Right, the amount of text the model can actually hold in its head at one time.
Exactly. So we're looking at a paper today that proposes a way to basically break the laws of physics, or at least, the laws of economics when it comes to training these large language models.
It does sound a bit like magic when you first read the abstract, honestly. The paper is titled Train Short, Test Long. Attention with linear biases enables input length extrapolation.
That is a mouthful.
Yeah, it is.
Yeah.
It's by Ofer Press, Noah Smith,
Yep.
and Mike Lewis. And that first part, the train short, test long bit.
It's a great hook.
It really is, because usually in machine learning, the golden rule is you train on exactly what you want to test on.
Right. So if you want a model to write a full novel, you'd better be training it on whole novels.
Exactly. But this paper comes along and says, actually, no, train it on a paragraph, and it'll just figure out the novel later.
Which sounds completely counterintuitive.
Totally.
Yeah.
But that is the core promise here. And to understand why that's such a massive deal for, anyone building these systems, we have to look at the actual cost of context.
Because everyone wants a model that can read a 50-page legal contract or a whole massive code base in one go. You just drag and drop it into the chat.
Right. And under the standard transformer architecture, which is what GPT and almost everything else is built on, the cost of paying attention to all that text doesn't scale in a straight line.
It's quadratic scaling, right? I think we've touched on this in previous deep dives.
Yes, exactly, quadratic. So if you double the length of the document you're feeding it, the computational work isn't twice as hard. It's
4 times as hard.
right. It gets incredibly expensive really fast.
Yeah.
So training a model on massive sequences requires a literal supercomputer.
Which most people don't have.
Exactly. So the mission of this paper is to essentially cheat that system. They developed this method called ALiBi.
Which stands for attention with linear biases.
Right. And ALiBi allows you to train on very short, cheap sequences, say just 512 tokens. But then at inference time, when you're actually using the bot,
When you deploy it.
yeah, when you deploy it, you can feed it thousands and thousands of tokens, and it just works perfectly.
So you're effectively getting a free lunch on context length.
Pretty much.
Okay, but before we get to this magical solution, let's unpack the problem a bit more. Why can't we just do this normally? Like, if I train a standard model on 2,000 words and then I try to feed it 2001 words, why does it break?
It's a great question. And it really comes down to how transformers perceive order. Because natively, a transformer is actually order invariant.
Meaning it doesn't care what order the words are in?
Right. If you feed it a completely scrambled sentence, the underlying math of the attention mechanism looks exactly the same as if it were a perfectly grammatical sentence.
So it just sees a bag of loose marbles.
Exactly, a bag of marbles, unless you explicitly stamp a number on each marble.
Okay, so we have to tell the model, hey, this is word 1, this is word 2.
Correct. And since the original attention is all you need paper back in 2017, the standard way to do this has been sinusoidal position embeddings.
Right, I've seen that term. What does it actually mean in practice?
Essentially, they add a mathematical wave pattern to the word representation. So it's like a unique signature for every single position in the sequence.
So position 500 has a specific flavor or a specific signature that the model learns to recognize during training.
Exactly. And during training, if your sequences are only 512 tokens long, the model learns the signatures for positions 1 through 512 perfectly.
Because it's seeing them over and over.
Right. It optimizes its weights to understand those specific signals.
Yeah.
But, and here's the massive failure point, what happens when you show it position 513?
It's never seen that signature before. It has no idea what to do with it.
Exactly. It has no idea. It's totally out of distribution. It's basically like driving off the edge of a map.
Wow.
Yeah, the paper shows that with these sinusoidal embeddings, as soon as you pass the training length, the perplexity, which is basically a measure of how confused the model is, it just explodes.
So it doesn't just degrade a little bit.
It becomes completely useless. It hits a brick wall.
Okay, so clearly this is a huge problem. People must have tried to fix this before ALiBi came along, right? What were the other options on the table?
Yeah, the authors do a great job of comparing their work against a few heavy hitters. The most famous one right now is probably rotary embeddings, or ROPE.
Rope, yeah. You see that everywhere in the open source community. Llama uses that, right?
Yes, exactly. Llama and a ton of modern open source models use ROPE. And it's a very solid method. It essentially rotates the vectors in a specific way that encodes relative position.
Okay.
And it's definitely better than the standard sinusoidal stuff. It doesn't crash immediately the second you go one token past the training limit.
But there's a catch.
There's always a catch. The authors of this paper argue that rope E still struggles to extrapolate indefinitely.
So it still degrades just further down the line.
Right. And plus, doing all that rotational math for every token adds a lot of computational overhead. It makes the model slower.
Got it. And they also looked at the T5 model, right? The one from Google?
Yes, the T5 bias method. Now, T5 is really interesting because it actually does extrapolate quite well. It can handle lengths much longer than what it saw in training.
Oh, really?
Yeah, but it achieves that by using learned parameters. It has to actually learn a specific weight for every distance bucket during training.
Which means it uses more memory.
More memory, and it takes significantly longer to train.
So it's slower.
Much slower.
Yeah.
So before ALiBi, you were kind of stuck in this classic pick two scenario.
Right.
You could have a model that extrapolates well like T5, a model that's fast like sinusoidal, or a model that's popular and decent like rotary, but nothing gave you infinite length without a massive speed or memory penalty.
So enter ALiBi. And what I find most fascinating about this approach is that they didn't add some crazy new complicated math. They actually removed something.
That's the truly radical part of this paper. ALiBi, attention with linear biases. Step one of their method is literally just delete the position embeddings.
Wait entirely, so you're back to the bag of marbles.
Exactly, back to the bag of marbles. At the input layer, the model has absolutely no idea which word came first.
That sounds like a terrible idea based on what we just talked about.
I know, right? But instead of putting the order information on the words themselves, ALiBi injects the concept of order directly into the attention mechanism.
Okay, let's visualize this for the listener. The attention mechanism is basically the model looking at two words, say a query and a key, and calculating a score of how relevant they are to each other.
Right, it's doing a dot product. And usually that score is purely based on content, like does the word bank match with the word river? What ALiBi does is simple arithmetic. It literally just subtracts a penalty from that relevance score, based purely on the physical distance between the two words.
So if the words are right next to each other, neighbors, the penalty is 0.
Effectively 0, yeah. But if the words are, say, 100 tokens apart, ALiBi subtracts a larger number from that score.
And if they're 1,000 tokens apart, it subtracts a huge number.
Exactly.
So it's essentially biasing the model to look at recent things. It's basically shouting, hey, the stuff right next to you is probably the most important.
Precisely. They call it an inductive bias towards recency. And the brilliance of it is that the model doesn't need to learn any position signatures at all.
Because it's hard-coded.
Right. The architecture itself forces the attention score to be lower simply because of the distance. It's a hard constraint, not a learned behavior.
Okay, now I have to play devil's advocate here.
Please do.
If you just hammer the model with a penalty for looking back in time, aren't you making it horribly short-sighted? I mean, the whole point of a long context model is that I want it to remember the detective introduced on page 1 when I'm reading the finale on page 50.
Right.
If ALiBi heavily penalizes that connection across 50 pages, won't the model just completely ignore the detective?
This is the most critical question about ALiBi, and the authors solved it in a very clever way. They leverage the fact that transformers don't just have one attention mechanism, they have multiple heads.
Right, multi-head attention. It's like having, 12 or 16 parallel brains working at once.
Exactly, and ALiBi doesn't apply the same penalty to every single head. It varies the slope of the penalty.
The slope?
Yeah, think of the slope as the harshness of the penalty. For some heads, the slope is very steep.
Okay.
So those heads are strictly focused on the last few words. They handle immediate grammar, local syntax, things like that.
But then you have other heads.
Where the slope is incredibly shallow, the penalty increases so slowly that the model can look back thousands and thousands of tokens with almost no cost.
Oh, I see. So those shallow heads effectively act as the long-term memory.
Yes, so it's a spectrum. Some parts of the artificial brain are short-term focused, and some are long-term focused.
That's elegant. And the best part is, you said earlier, these slopes aren't learned during training.
Not at all. The model doesn't have to figure them out. They use a fixed geometric sequence.
Like what?
Like 1/2 to the first power, then 1/2 squared, 1/2 cubed, and so on.
So you type it in the code once and you never touch it again.
Exactly.
That seems incredibly rigid for modern AI, though.
Right.
Usually the whole philosophy is let the neural network learn everything from the data. Why hard code something so important?
2 reasons. efficiency, and robustness. By hard-coding it, you completely remove those parameters. You don't have to train them. You don't have to store them in memory.
Which saves VRAM.
Huge amounts of VRAM. And as we'll see in the results, it turns out this specific geometric decay actually works across almost any type of text you throw at it.
Well, let's talk about those results then, because train short, test long is a very bold claim to put in the paper title. Did it actually work?
It worked shockingly well.
Yeah.
So they ran experiments on the Wikitext 103 benchmark. They trained an ALiBi model on sequences of only 512 tokens.
Which is tiny by today's standards.
Tiny. And then they tested it on much, much longer sequences.
And compared it to the standard sinusoidal stuff.
Right. They compared it to a baseline sinusoidal model that was trained on 3,072 tokens. So exactly 6 times the training length.
And who won?
ALiBi won.
Really?
Yeah. The ALiBi model trained on the short, cheap 512 token sequences actually achieved better perplexity, meaning it was less confused than the model that had been trained on the long 3,000 token sequences.
That feels entirely counterintuitive. How can a model that saw significantly less context during its training be better at actually using context in the real world?
Because the sinusoidal model overfits to its training length. It learns position 3000 as a very specific, rigid concept.
Okay.
If it hasn't seen that specific position enough times, it struggles. But ALiBi doesn't learn absolute positions. It learns relative distance.
Whoa.
And relative distance is the exact same concept whether you're at token 500 or token 50,000. One word back is always just one word back.
It generalizes perfectly because the rule is purely relative.
Exactly. And the efficiency gains they got from this are just massive. Because they trained on 512 tokens instead of 3,000, the ALiBi model was 1.84 times faster to train.
You're almost cutting the entire training time in half.
Which is huge.
Yeah.
If you're a startup burning venture capital on GPU cloud hours or a researcher with a strict budget, that is literally the difference between shipping a product and running out of cash.
And they didn't just test this on small toy models, right? They scaled it up to prove it works in the big leagues.
They did. They trained a 1.3 billion parameter model on the CC100 plus Roberta corpus. That's about 461 gigabytes in text.
Serious data.
Yeah. And they compared an ALiBi model trained on 1,024 tokens against a baseline trained on 2,048 tokens.
And what were the stats there?
Same perplexity, same exact performance quality, but the ALiBi model was 11% faster to train and used 11% less memory.
Now, 11% memory savings might sound a bit boring to a non-technical listener, like,
Yeah.
oh, great, you saved a gigabyte. But in the world of high-end AI training on GPUs, VRAM is absolutely everything, isn't it?
It is the ultimate bottleneck. In their specific hardware setup, they save between 1.6 and 3.1 gigabytes of VRAM per GPU.
Wow.
And when you're training these giant models, you're constantly dancing right on the edge of getting an out-of-memory error and crashing the whole run.
Right.
So saving 3 gigabytes means you can increase your batch size, you can make the neural net deeper, or you can just run it on slightly cheaper hardware. It is valid, massive operational leverage.
And what about speed when you're actually using the model, the inference speed? Because you mentioned earlier that T5 bias works for long context, but it's really slow.
ALiBi is effectively free at runtime. The authors point out that implementing ALiBi is just changing a few lines of code in the mask matrix of the attention layer.
So no complex math.
None. It adds 0 overhead compared to a standard baseline model. It is faster than T5 bias, and it's noticeably faster than rotary.
Okay, so let me get this straight. It's fast, it's cheap to train, and it works on infinite context. But I want to do a deeper dive into the why here. Because the paper mentions this concept called the early token curse.
Yes.
Which honestly sounds like an Indiana Jones movie title.
It really does. But it's actually a very real, very annoying problem in how we train language models.
Walk us through it. What is the curse?
Okay, so imagine you have a giant book you want to train on. To feed it to the model, you have to chop that book into manageable chunks. Let's say chunks of 512 words.
Right, non-overlapping chunks usually.
Exactly. Now look at the very first chunk. The first 50 words of that chunk have almost no history to look back on.
Because they're at the very beginning.
Right. They're flying blind. The model struggles to predict them because there is no established context yet.
Like if the sentence is, he walked into the room, but it's the first sentence of the chunk, I don't know who he is.
Precisely. Now fast forward to the second chunk. In the actual book, the first word of chunk 2 comes immediately after the last word of chunk 1.
The story continues continuously.
But the model doesn't see that during training. It completely resets. It treats the start of chunk 2 as a totally blank slate.
Oh, wow. So every time you start a new training chunk, the model basically gets amnesia.
Yes, that amnesia is the early token curse. A model trained on short sequences spends a massive percentage of its life suffering from this lack of context.
And a model trained on longer sequences suffers from it less often, simply because the chunks are bigger, so there are fewer resets.
Exactly.
Yeah.
So the authors hypothesize that the reason long context training usually results in better models isn't necessarily because the model is learning brilliant long-term reasoning.
It's just because it's not getting amnesia as often.
Exactly. They used a sliding window analysis to prove this. ALiBi allows the model to act like it has a continuous sliding window during inference.
Because the attention is relative.
Right, you never have to reset. When you get to token 1000, the model just naturally looks back at token 999, 9998, and so on without any boundary issues.
It creates a seamless stream instead of these choppy, disconnected blocks.
Yes. And the visualization they included in the paper figure 3 shows this perfectly. It's a heat map of the attention.
What does it look like?
The diagonal is incredibly bright, which means there's very high attention paid to recent words. And then as you move away from the diagonal, it gets darker in a perfectly linear way.
So it's a soft window that just slides along with the text as you read.
Exactly. It effectively cures the early token curse, but without needing the massive compute cost of training on long sequences.
And this method turned out to be surprisingly robust, right? I remember reading about the domain transfer experiment they did, which kind of blew my mind.
Yeah, that was honestly the mic drop moment in the paper for me
Right.
regarding the universality of this ALiBi method.
Tell us about that.
So they took the slope settings, that specific geometric sequence of penalties that they originally optimized for the Wikitext dataset.
Which is, factual, encyclopedic, very structured stuff.
Right. And they applied those exact same penalty settings to the books corpus dataset.
Which is totally different. Novels, dialogue, fiction.
Completely different structure, different vocabulary.
So did they have to tune the slopes? Like, did they say, oh, fiction needs a steeper slope because dialogue is punchy?
Not a single digit. They didn't change a thing. They used the exact same setup from Wikitext, and it worked perfectly on the books. It outperformed the baselines again.
That is wild to me. It almost implies that there's a fundamental shape to how human language works.
It really does. It strongly suggests that regardless of whether you're reading a dense physics paper or a trashy romance novel, the relevance of a previous word decays over distance in a predictable geometric way.
And ALiBi essentially hard codes that fundamental law of language directly into the model's architecture.
Exactly.
Okay, so we have a method that is cheaper, it's faster, it saves huge amounts of memory, and it seems to capture a universal law of text.
It's a huge win.
But, nothing is perfect. We always have to look at the trade-offs on this show. And the authors themselves actually bring up a really provocative question right at the end of the paper.
They do.
Yeah.
And it centers on the very subtle difference between a model not crashing and a model actually reasoning.
Explain that distinction for us.
So ALiBi successfully prevents the model from failing on long texts. It stops the perplexity from exploding because it strictly biases the attention toward the immediate neighbors.
It keeps the car on the road.
It keeps the car on the road, yes.
Yeah.
But does it actually allow the driver to see the horizon?
Ah. So if I have a specific crucial piece of information, a needle in the haystack, and it appeared 50,000 tokens ago in the text, and I ask the model a complex question that requires retrieving that specific needle, if ALiBi is constantly applying a heavy mathematical penalty to that distance.
The model might just miss it entirely. The bias toward recency is a double-edged sword. It stabilizes the model so it doesn't crash, but it technically discourages the model from looking closely at very distant tokens.
But wait, didn't we say earlier that the shallow heads handle that? The heads with the really low slope.
They do, and theoretically those heads should catch it. But the bias, however small, is still there.
Right.
Think about it. A standard model with no bias treats token 50,000 with the exact same potential importance as token 5. ALiBi inherently says token 50,000 is probably noise unless it's really, really undeniably important.
So ALiBi is an incredibly robust way of handling local context and flow. It ensures the model can read a whole book without hallucinating wildly or crashing your GPU.
Yeah.
But it might not be the ultimate final solution for complex reasoning tasks that require effortlessly connecting two tiny dots separated by 1,000 pages.
Exactly. It completely solves the length problem, the purely mechanical ability to ingest massive data without crashing. But the reasoning problem over that massive length is still an open frontier in AI.
That distinction is so important. It's the difference between saying, I read the whole book and I perfectly remember the footnote on page 42 and how it connects to chapter 10.
Correct. But if you think about most actual use cases right now, summarization, coding assistance, general chatting, the local context is usually what matters most anyway.
Yeah, that's true.
So for 99% of applications, ALiBi is just a massive, unambiguous win.
And it democratizes the capability. That's the part I keep coming back to.
Absolutely. Train short, test long breaks the restrictive link between your training budget and your inference capability.
You don't need a massive cluster of H100s to train a model that can read a novel anymore.
Right. You can train on shorter sequences, on much more modest hardware, and still deploy a model that handles massive enterprise-level contexts.
It effectively future-proofs the model. You train it today on what you can actually afford, and tomorrow it can handle inputs longer than you ever imagined.
It's a shift from just brute force, just add more compute, to actual architectural elegance. It's using a smarter inductive bias to get significantly more out of less.
So if you're a listener working in this space or even just casually watching the AI race, why does this specific paper matter to you personally?
I'd say if you're evaluating or choosing models to use for your projects, look under the hood. If a model uses ALiBi or similar linear biases, it's a very good sign that it will be highly robust on long documents.
And probably more efficient to run.
Exactly. It also signals that the creators of that model actually cared about optimizing for real-world inference, not just chasing training metrics on a leaderboard.
It's a sign of a genuinely well-engineered model.
Completely agree.
Well, I think that's a perfect place to wrap up. We've gone all the way from the early token curse to the free lunch of linear biases. It's pretty rare we get to discuss a paper that offers such a clear win-win for both efficiency and performance.
It really is. It's just a very satisfying piece of engineering all around.
A huge thank you to Press, Smith, and Lewis for publishing this incredible work. And to you, our listeners, next time you feed a massive 50-page PDF into a chatbot and it magically doesn't crash, you might just have ALiBi to thank.
Indeed you might.
Thanks for listening to this deep dive. We'll see you on the next one.